All right, this is lesson 8-4. It's on quadratic story problems still. This is the second of these videos. The 8-3 was the first one. One thing to keep in mind as we're studying these, let me add a page in here, is that oftentimes when we're looking at a graph of this situation, it's going to look something like this. And usually we'll say that this bottom line is representative of time, where time is 0 at this spot and then moves forward, headed that direction. And then we'll say that this axis, the vertical axis, represents height. This isn't how all, let me see if I can write that better. This isn't how all quadratic story problems behave, but a lot of them do. So if it behaves like this, I want to point out a few things. There are several pieces of information we can glean from this look. One, it's got a negative a value. You can see that the quadratic's opening down. And because of that, it has a highest point, the maximum point. And we've studied how to find the maximum before. We've been doing that for actually quite a long time. And the vertex is a key piece of information that's going to help us determine where the maximum occurs. So the vertex is an ordered pair, right? It's telling us how far over, so it can tell us the time when we reach the maximum height. But then we'll also find out how high that maximum height is. So just a reminder that to find the vertex, we can use opposite of b over 2a, and then to get the second number in the vertex, we plug that first number in to the equation and it tells us what it is. So usually this first number tells us how long it took for the object to reach the maximum height. And the second number tells us how high that item actually was. So the ordered pair tells us how far to go to the right and then how far to go vertically. Okay, other things that we can find from graphs like this, we can identify this place. This is the y-axis, but in our story problems, it might be something about how high the item was before it was maybe thrown or kicked or whatever like that. So the starting point, height, right? This is the c value. C is the y-intercept. And that makes intuitive sense if we think about the fact that looking at a quadratic equation like ax squared plus bx plus c, that if we replace the x's with 0, then ax squared becomes 0, bx becomes 0, so the only thing left is c, and that's telling us this spot, how high something occurred. Okay, so those are a couple of good pieces of information. The final one is probably the most frequent, and that is determining how long it takes for something to hit the ground. Okay, now this spot is the x-intercept, which we also call the 0. Sometimes it's called a root. Sometimes it's called the solution. Okay, so we have a lot of methods for finding the solution to these things. We can factor, take the square root, complete the square, and probably the one that we'll use most often today, complete the square, sorry about that, is the quadratic formula. So when we want to find that place of where or how long it takes for something to hit the ground, is often what the story problem's about, then the quadratic formula will help us to find that. Now we want to draw your attention over here. There's a second x-intercept 0 root solution. If we're dealing with time, then this answer is going to be a throwaway answer because that would require us traveling backward in time, and so it doesn't fit sort of the world we live in, so that's an answer that we will ignore. Often it's the negative solution that we yield from a problem. Okay, so that's sort of some background on what we're looking at and what we have access to when we're doing these types of problems. So let's hop over to our notes and see what it's talking about here. It says, remember the vertex of a quadratic equation written in standard form looks like that. So they just wanted to draw our attention back to the fact that we have used a vertex before and it is useful for us sometimes. Let's read this first problem and see what we can do with it. A soccer ball is kicked from the ground with an initial upward velocity of 90 feet per second. That, by the way, is in the problem. Okay, so it's not an additional piece of information that we need to. It's already in there. The equation h of t equals negative 16t squared plus 90t gives the height h. We talked about height, didn't we? So this axis is the height of the ball after t seconds. This is time. So this fits the story that we were just describing on that other page. I'm not going to worry about that 90 up there. It's already in the story problem. They're just giving us some in the equation, excuse me. They're just giving us some background information to tell us about it. So somebody kicked a ball and they kicked it pretty hard, maybe 90 feet per second. I don't really have a concept of how much that is, but you know, you can imagine a person right here, they come up and kick the ball, it goes up, 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 and then it lands, okay? So they may want to know how high was its highest part, how long did it take to get to the highest part, how long was it in the air until it landed on the ground. These are all things that we can discover together. So let's take a look. How many seconds will it take for the ball to reach its maximum height? Okay, maximum is key. It's super helpful because maximum is something that we can find using quadratic equation. So just remember that in standard form, the quadratic equation looks like ax squared plus bx plus c equals 0. So when I refer to an a or a b or a c, I'm talking about if the quadratic's in standard form. A is the coefficient of the quadratic term, b the coefficient of the linear term, and c is the constant. Okay, so in this story, a is negative 16, right? Because the quadratic term, t squared, is right there. And b is 90. So there's the linear term. Okay, remember that if we want the maximum, the vertex is going to help us get there. So we just reminded ourselves that negative b over 2a is the useful vertex. So I'm going to replace the b with 90 and replace a with negative 16. It's actually not a bad idea to do both of them in parentheses. Let me calculate that real quick. I got a decimal answer of 2.8125. Because that's not a lot of decimals, then I'm going to keep that whole thing and it won't be a problem. How long will it take for the ball to reach its maximum height? That's going to be the first number in the vertex, how long it takes for it to reach it. So that's what we found. It's going to take 2.8125 seconds for the ball to reach its maximum height. Okay, the second question also is referring to maximum. It says, what's the maximum height of the ball? So now we want to know, how high did it travel? So to find that, we're going to plug this into the equation. I'm going to replace every t with 2.8125. And we'll hit this in the calculator. And we get 126.5625. So that tells us how high the ball went at its highest, the maximum height of the ball when it was kicked, at its highest spot, I guess. So let's see, this is feet per second, so this must be referring to the maximum height that it reached in feet, 126.5625. I have no concept of if this is accurate or not. Do people kick balls that high? Maybe they do. I don't know that I could. Okay, finally, this one asks for the domain and range of the function. I'm going to pop back over to the picture that I did on the other page, if I can find it. Here it is. The domain is referring to the x-axis, so when we move from the left to the right. So in the story, time starts at 0, so our domain is going to go from 0 until we get to where the ball lands on the ground. That's the domain we're going to deal with. Now, when we've talked about domain and range in the past, we said that for quadratic equations, the domain was negative infinity to infinity, and it always is, which is true. But when we're dealing with a story problem, we want to limit the domain to the things that make sense. So if you think of negative infinity as traveling backwards in time as far as forever, it doesn't really make sense in the concept of the world that we're living in. But starting from when the ball is kicked until it lands on the ground, that's a piece that we can handle. So that's what we're going to talk about. So 0 makes sense for one of our answers on this one. And then we also want to find this spot. Okay, so that spot is key. It can be found, it's our x-intercept, 0, root, solution. We can use the quadratic formula to find that. So we will in just a second. And then, what color haven't I used? This pink maybe. To find the range, this is from low to high. Now, the range is always limited with parabolas, with quadratics. But we're going to limit it even more. We're going to say, okay, from the height, maybe 0, from ground level up until it reaches its highest point. And you may know we've already discovered that. When we found its maximum, we found some good information about the range. So maybe let's go fill that in very first off. Headed the wrong direction. Here it is. Okay, so the range, this is from low to high. The range in this case is from 0 to our maximum height, 126.5625 feet. There's our range, so that's taken care of. Let's do the domain. So to find the domain, when does the ball hit the ground, what we're going to need to do is solve this equation. So I'm going to go ahead and use the quadratic formula. In this case, our variable is t, so t equals negative b plus or minus the square root of b squared minus 4ac. Notice that we don't have a c. It's missing. I guess I'm underlining where c would be. We don't have a constant in this problem, so I'm going to replace that with a 0 in the formula all over to a. Okay, let's start by finding the discriminant first. So I'm plugging this stuff into my calculator without the radical symbol, just that stuff. And it gives us 8100. So if I simplify just a little bit, I get that t equals negative 90 plus or minus the square root of 8100 all over negative 32. Now, it's really easy to make errors along the way, so even though 8100 is going to square root of 8100 is going to simplify here pretty quickly, I think it's worth writing it down just so if you're comparing work with a neighbor or something, then you can see if you at least got that step correctly. It's really easy to make errors there. Now, the square root of 8100 is 90. So for this one, we're going to have negative 90 plus or minus, whoops, now square root again, 90 over negative 32. All the numbers have gone away, so now we have two situations, and I'm going to expand this. One situation is when we're doing negative 90 plus 90 over negative 32, and negative 90 plus 90 is 0, and 0 divided by negative 32 is 0. The other situation is negative 90 minus 90 over negative 32. Okay, so we're taking into account both the positive and the negative that we've got right there. Negative 90 minus 90 is negative 180. Negative 180 divided by negative 32 is going to be 5.625. So that tells us how long the ball was in the air until it hit the ground. So our domain for this problem is going to be from 0 until the ball hit the ground, 5.625. All right, let's try another problem. This one says, a diver is standing on a platform 25 feet above the pool. He jumps from the platform at an initial velocity of 10 feet per second. Okay, if you were in my class, I told you I'm just going to provide you with the formula and you don't need to worry about it. But let me just show you how this works in case you're interested. This h sub 0, is referring to the initial height. So when the story begins, How high was the person from the ground, maybe? And they told us that it's 25 feet. So I'm going to replace this h with 25. Then this v sub naught, or at the initial velocity, when time was 0, or just after time was 0, I guess, what was the velocity? And they're telling us that it was 10. So as I told you, if you're in my class, I'm just going to provide you with the information. I feel like this is a little bit to ask of my regular math students, but so this is the equation that we've got here, and it's based on the information they gave us from the story. Okay, so we have our equation. I think that's all that this first part wanted. If I were drawing a picture of what's happening, here's ground level. There's a diving board right here, 25 feet above the air. At time 0, the person's going to jump and then go into the pool. Okay. So now it says, find the diver's height after 2 seconds. Okay, so one of the ways that we can do this is replace the t with 2. We want to know at 2 seconds what happens. Yeah. So I'm going to go ahead and replace t with 2, and that will tell us the height at 2 seconds. Negative 16 times 2 squared plus 10 times 2 plus 25. This is giving me negative 19. So at 2 seconds, my person is going to be negative 19 feet from ground level. So let's look at our story. Does it make sense that it would be negative? Well, I guess so, because they're going to land in the pool and go down. Now, I don't know how deep the pool is, and once they get to the water, it's going to slow down their progress and stuff like that. But according to our quadratic formula, in 2 seconds, the person's going to reach negative 19 feet. So pretty fast dive, I guess. All right, let's take a glance at the assignment, and I'll just guide you along on a few things. On the first problem, they talk about 128 feet per second. They talk about a 12-foot platform. Those are already in the formula, okay? So we don't need to stress about those. They're just background information for you to have, okay? The question it says is, how long will it take the rocket to reach the ground? How long to reach the ground? Okay, so we want to know the length of time that it takes until we get to there. So we want our x-intercept, or our solution, or our 0, or any of those. So to solve this one, I recommend using quadratic formula. If you get a positive answer and a negative answer, you probably want to use, well, you certainly want to use just the positive answer. That's time after the launch. Before that, it's backwards in time before the launch occurred. Okay. For story problems, you generally want a decimal approximation rather than a simplified expression. So go ahead and take the square root, even if it doesn't give us a nice clean radical. We want a decimal number for the solution here. Show your work as you go. I want to see the quadratic formula here. I want to see that you simplified the discriminant, right? So there is certainly work to be shown as you move along. This one talks about a penny dropped from the Empire State Building. If the penny's pathway can be modeled by this equation, see the 1250, refer to the 1250 there, okay? How long will it take for the penny to strike a 6-foot tall person? So in this case, we're not wondering when it hits the ground, but instead when it falls, and suppose it hits a 6-foot tall person right on the tip top of their head before landing to the ground or anything like that. So for this problem, we don't want to know when it hits 0. We want to know when it hits 6 feet. So let's replace this height, h of t, with 6. Then put this equation in standard form and solve it. Since this, or just solve it. Since this doesn't have a linear term, notice that there's a constant, no variable, quadratic, another constant. This one might be easiest solved using the square root method. Okay, again, we only want the positive answer. We're looking for how long it takes, so time moving forward. Some fireworks are fired vertically into the air from the ground, so at 0, at an initial speed of 80 feet per second. Write an equation modeling this. I'm going to give you the equation. we'll say that the height at time t is represented by negative 16t squared. They gave an initial velocity of 80 feet, and then they said it's from the ground, so we could put plus 0, or we could just leave that off. They want the domain of this function. So remember that as far as our picture goes, the domain is from when they fire the firecracker until whenever it hits the ground. Okay, so it's going up and then it hits the ground at some point. So your domain we're going to solve again, okay, using maybe the quadratic formula on this one. And it's going to be from time 0 until whenever it hits the ground. Okay, I hope that these are helping a little bit. Over here they're saying maximum height. So remember that for a maximum, we want to use our vertex, right? That's negative b over 2a, and then plug it in. Here, Eva's jumping on a trampoline. We want to know if she's going to reach 14 feet. So there's two strategies for this one. You could replace the height with 14 and then solve, or you could find the vertex and see if the maximum gets above 14. So either of those methods is a good one. Just make sure that you follow it to its conclusion. And finally, we have this story about a person throwing a baseball on the moon and then throwing a baseball on Earth. And of course, on the moon, because gravity is a lot less powerful on the moon, I don't know the right terminology, then the ball is going to stay in the air quite a bit longer. So we're going to need to find out how long the ball will be in the air for both equations. So you got to solve each of them. Remember that how long the ball is in the air sort of models this situation. We're trying to find that spot. Okay, so quadratic formula would be a good one here. We want the positive solution. Once you get both solutions, then we want to know how much longer one thing would be than the other. So you're going to take the big number minus the little number, right? And that will tell us how long it was on the moon. Okay, good luck.